Hey class, this is Mr. Roberts at Shasta High School, and time to look at some homework. This is chapter 3. We're looking at, I think, questions through 8 through 13 in this set. And let's start with number 8. It says a three-dimensional shape at right is called a cylinder. Or cylinder, sorry. Its bottom and top bases are the same size circles, and its, quote, side is perpendicular to the base. What would the shape of a flag need to be in order to generate a cylinder when it spins about its pole? You may want to refer to that problem in the class with the triangular flag that produced a cone, right? So if this is a stick or a pole or something, I could rotate around this object, right? And as I spin this really fast, right? If I had, for example, this little flag that looked like this, right? As this thing went around and around, right, it would go around this way. Oops, around this way. And as it did that, this would start to look like a cylinder. Mr. Roberts, that's probably one of the worst drawings I've ever seen you do. You're right, that was terrible. So instead, I just decided to draw this flag inside of the diagram that was in our book. So this shape right here, if this was our flag, if I spin this around, I'm going to get this shape that looks like a cylinder, right? It's got circles that are the same on the top and bottom, and the sides are perpendicular to those bases. Let's move on to question number 9. It says, graph each line below on the same set of axes. So there are three different functions here, and they're all called f, right? Clearly, that's not a great thing because if we were going to mix them up or do things with them, it'd be nice to know that they had different names. But let's graph them separately. So a, right? A is the function f that it has the expression 3x minus 3. So this is going to begin with a y-intercept at negative 3. Put the little dot here. And then it has this slope pattern of up 3 over 1. So from here I could go up 1, 2, 3, and then over 1. Up 1, 2, 3, and over 1. Up 1, 2, 3, and over 1. So this is the pattern for A. And if I grab the ruler and put the lines that go through those dots, that's roughly what we're looking at. This is function a, y, f of x equals 3x minus 3. Let's look at the next function. This one has a y-intercept that starts at positive 3. The last one was at negative 3. And it has a slope pattern that's down 2 over 3. So starting at positive 3, I can begin here, right? And then I'm going to go down 2 units and then over 1, 2, and 3 units right here. And then I'll go down 1, 2 units and over 1, 2, 3 units right there. So there we go. Going to go ahead and line this up. And I will grab my ruler tool and just draw the line that goes through that. It continues in both directions indefinitely, so I'm putting these arrows in here to indicate that. So that's my third function, f of x equals negative 2/3 x plus 3. The last function has a y-intercept that sits way up at 5. Put a dot here at 0, 5. Fortunately, these are all in slope-intercept form. And then it has the pattern down 4 over 1. So from the 5, I'm going to go down 1, 2, 3, and 4, place a dot, and then I'm going to go over 1 unit. Oops, don't need that. Over 1 unit. So this is my next point. Then I'll go down 1, 2, 3, 4 over 1 unit. There we go. And I'll do one more down 1, 2, 3, 4 units and over 1. So this, I think, is the steepest of the lines. It does have a negative slope, but it's still steeper, right? The absolute value of its slope is greater than any of the other slopes. So there we go. That's our third function. And we now have those three functions graphed on a single set of axes. Let's move to question 10. Question 10 says AC is a straight segment as shown in the diagram. If the distance between points A and C is 76 miles, determine the distance between points A and B. So we're asked to figure out how long this distance is from point A to point B. And we are also told that the distance from point A all the way to point C is 67 miles. So just using this, right, the distance from A to B, which is 5x minus 2, plus the distance from B to C, which is plus 2x plus 6 is equal to 67 miles. If I collect my like terms, I have 7x here. Negative 2 and 6 is going to be a plus 4, and that is 67. If I take away 4 from both sides, I get 7x is equal to 63. And then if I divide both sides by 7, x is 63 over 7. I don't think that's divisible. Not nicely anyway. 63 over 7 is, oh, it's, Robert, you're kidding me, right? 9 times 7, 63. Yeah, this is 9. So x is 9. Now, let's go back up and look at what question I was asked. They didn't ask me to find x. I was asked to find the distance between points A and B. So here's the thing. I know that algebraically we're representing the distance between points A and B as 5x minus 2. And I know that x is the number 9. So I'm just going to plug in that value of x. So I've got 5 times the 9 minus 7. 5 times 9 is 45. And then 5 times 9 is 45. Minus 7 is going to give me 38. So 38 miles, M-I-L-E-S, is the distance. Moving on to question 11. Oh, put your calculator away. This icon over here says, do this without your calculator, right? It's good for you. You could check your answer with it if you want at the end. But I'm going to add these numbers with no calculator. So let's start. For A, I've got a 10, and I also have a negative 9. And I also have a 7/9, and I also have a negative 2/3. This is one of the things that's kind of interesting about mixed numbers, right? This negative 9 and 2/3 is literally a negative 9 and a negative 2/3. So the whole fraction's negative, so that's why it's 7/9 minus 2/3. 10 minus 9 is 1, and I've got 7/9 minus 2/3. I'm going to turn this 2/3 into ninths by multiplying it by 3 over 3. Again, big idea, right? Anytime I see a value, I could multiply it by 1, any form of the number 1 I want, and it doesn't change its value, it just changes its form. So I'm going from 2/3, and when I do that, this becomes minus 6/3, right? So I've got 1 and 7/9 minus, oh, no, not 6/3, 6/9. Hello. 2 times 3 is 9, or 2 times 3 is 6, and 3 times 3 is 9. So this 2/3 becomes 6/9 when I multiply it by the giant 1 of the form 3 over 3. So 1 plus 7/9 minus 6/9 is going to be 1, and just 1/9 positive. And you can do 1 times 9 is 10, plus 1 is, you can write it as 11/9 also. So A, I've got 1 and 1/9 or 11/9. Let's look at B. So B, we have a negative 10 and we have a negative 2. So you can see I'm grabbing those whole numbers. I just want to look at them separately. Then I've got this negative 7/10 and I've got a negative 3/5. That's why I'm not a fan of the mixed numbers, is because we may not know that both of those are negative, but it is, right? It's a negative 2 and a negative 2/3. Let's see, negative 10 and negative 2 is negative 12. And then I'm going to change this negative 3/5 by multiplying this by, wait for it, maybe you guessed it, 2 over 2. And the reason why I selected 2 is it's going to make this denominator match the denominator for 7/10. So when I do that now, I have the minus 7/10. And then I have a minus 6/10, right? 3 times 2 is 6, and 5 times 2 is 10. So this is beautiful, right? I can totally do this. This is a negative 12 minus 13/10. Interesting, 13/10, right? That is an improper fraction, but because I've got this whole number, I want to pull out the whole number and combine it with the 12. I'm not going to leave it like this. So this is a negative 12, and then I'm going to, I'll pull out 3/10, so it's going to be a minus 3/10 and a minus 10/10. tenths. So what I did is I just took the fact that I had this negative 13 tenths and I broke it up into the sum of two pieces, negative 3 tenths plus negative 10 tenths. And you can see if you put those back together, it is negative 13 tenths. So now this negative 10 tenths is the number 1. I'm not multiplying by it, I'm subtracting it. But I have a negative 12 and another negative 1, so this is negative 13 and minus 3 tenths. And I can use this mixed number notation. My final answer is negative 13 and 3 tenths. And that's probably a good enough answer for now. So negative 13 and 3 tenths. Let's move on to question C. Running out of room a little bit. When I see that I'm multiplying or dividing and I have mixed numbers, I almost always go to improper fractions. So I'm going to make that conversion here. I've got 4.5. That's equal to 9 halves, right? 4.5 is 9 halves. And you know shortcuts that you've seen to do that in elementary school. 4 times 2 is 8. So I've got 8 halves. And then plus 1 more is 9 halves. And I'm going to be subtracting from that. That's negative 33 tenths. So negative 33 tenths. Okay, so I'm not subtracting anything. I've got that, and I'm going to be multiplying by, there we go, that's what I'm doing. So 10 times negative 3 is negative 30, and then another negative 3 is negative 33 tenths. All right, so let's clean this up. I don't see anything really happening here. 33 divided by 2 is not, it's not a whole number, right? And 9 over 10, there's no common factors there. So I think I'm going to just go ahead and go 9 times negative 33, which is negative 297. And then I'm going to go ahead and multiply 2 times 10, which is 20. And because there were no common factors there, I mean, this is literally 3 times 3, and this is literally 3 times 11. And I look at the bottom, I don't have any factors of 3. The 10 is 2 times 5. So there's no common factors. This fraction actually cannot be reduced. So not having a calculator, I'm going to leave my answer in that form. So it's negative 297 over 20. Last question, and boy, there's no room for it. Let me write it over here. So this is part D, and it's negative 8 and 3/5, and I'm going to divide negative 8 and 3/5 by 1 and 1/5. Negative 8 and 3/5 divided by 1 and 1/5. So let's just get over here. We can look at this by itself. Again, multiplication or division, I'm always going to switch to improper fractions. So if I've got negative 8 and 3/5, negative 8 times 5 is negative 40. And negative 40 and negative 3 is, this should be negative 43 fifths. 8 times 5 is 40. 1, 2, 3. Yeah, negative 43 fifths. And I'm going to be dividing by 5 6/5. Right, the number 1 is 5/5, so that's 5/5 and 1/5 is 6/5. And to do this division, I am going to multiply by the reciprocal. So I've got negative 43 fifths. I'm going to multiply that by 5 sixths. This does form a giant 1, right? 5 over 5 is equal to 1, so I'm left with, in my numerator, a negative 43, and in my denominator, a positive 6. Pretty sure that 43 is not divisible by 6. No. So we're going to leave our answer there, negative 43 over 6. You can go to a mixed number if you want, but honestly, I always prefer the improper fractions. Next question. Oops, this has got a lot of text, and I apologize that it's hard to see on this screen. Number 12. Mr. Saxon is concerned about his students' scores on the last math test and about the number of students looking tired in class. He decides to see if there's a relationship between the number of tired or sleepy behaviors, yawns, nodding off, head on desk, a student exhibits and their test score. He has his assistant observe 10 students and count the number of tired behaviors during 1 week of class. Hmm. So we've got this table that's recording the number of tired behaviors and the number of test scores. And part A says make a scatter plot on graph paper and draw a line of best fit. Determine the equation of the line of best fit. So looking at this table, I can see that the tired behaviors ranged from 0 to 7. So I set up my x-axis as I labeled it sleepy behaviors, and I had 0, 1, 2, 3, 4, 5, 6, and 7 there. And then for test scores, I ranged from 0 up to 100. And I just need to plot these points now. And the first one I'll plot is the fact that 2 goes to 73. So at 2, I'm right up here, very close to 70, around 73. So I went through and I carefully plotted all those points. One of the points, 190, occurred twice, so I put a little 2x there by it. But in general, I kind of see a pattern here. So if I'm going to sketch a line of best fit, I'm just going to grab my ruler tool, and I just kind of want to line it up so that it's roughly fitting the same direction that I see this data is moving along. And I think, and somewhere in here, I'm gonna settle on a spot, right? And I'll just, this is clearly not what we're going to be doing later. There's other tools that we'll have for looking at finding lines of best fit, but this is a pretty good start. And notice that my line isn't actually hitting really any of the points that I had. Maybe it should be a little bit higher, but I'm going to go with this point. And this line, and what I'm going to do is I'm going to pick 2 points that I'm relatively sure that are on the line and use those points to describe the equation line. So for example, if I look at this point here, this is 2 sleepy behaviors and a score of 80. And if I look at the point right, I don't see another great one. I could do this. It's a little awkward. It's 3.5 sleepy behaviors. Not quite a sleepy behavior, but 3.5 sleepy behaviors and a score of 70. Those 2 points are the points that I'm going to use to figure out what this line of best fit is. So think about this conceptually, right? We've plotted our points and we say, hey, this line looks like it approximates what we see happening. In general, the more sleepy behaviors we see, the test scores tend to be a little bit lower. And it turns out the 2 points I've marked in blue kind of identify this line, right? And the points are located at x is 2, y is 80. And the other point is x is 3.5 and y is 70. So those 2 points I could use to determine the equation of the line, right? Because that's what the final part says. And this is the thing where it's good because we get to practice what we've been doing in class, right? It says use your equation from part A. Well, we haven't come up with it yet, right? But we've drawn our line of best fit, and it says determine the equation of the line of best fit. So let's come over here and just focus on that. So we know that in order to get this equation, we need to be able to describe how much y is changing. It's decreasing. We know it's going down, divided by how much x is changing. I can see that y was at 80 and it went to 70. And if I was to do that subtraction, right, 70 minus 80, I see that y decreased by 10 units. And for x, I can see that x is at 3.5. It ends up at 3.5 and began at 2. 3.5 minus 2 is 1.5. So I've got this 1.5. So I have negative 10 divided by 1.5, negative 10 divided by 1.5. And when I do that, I get 6 2/3 negative, and my preference is to go ahead and just express that as the fraction negative 20/3. So this is negative 20 over 3. So down 20 over 3 units. That's what I'm describing as the slope of this line, right? This is the slope of the line. Now, that's great, but I need to also find the y-intercept. And the way that we've been doing in this class, I can see on the graph that the y-intercept is somewhere between 90 and 100. So I'm going to really be surprised if I get a y-intercept that is not in that range between 90 and 100. But let's go ahead and just take a moment and do this. And we'll go ahead and do this with the slope-intercept form again. We'll talk about other options later, but I'm writing down y equals mx plus b, and I'm going to choose to use the first point here. X is 2, y is 80. It has a y value of 80, so I put 80 in for y. My slope is negative 20 over 3, and my x value is 2, and then I've got the plus b. So 80 is negative 40 over 3 plus b. So then I'm going to write 80 plus 40 over 3 is b. So you can see from that, the second to the last step to this last step, what I did was I added 40 thirds to both sides. I'm going to go ahead and turn 40 thirds. I'm going to turn 80 into 40 thirds. I'm going to do that by multiplying this number 80 by 3 over 3. Totally can multiply something by 1 and not change its value. 3 times 8 is 240, and then over 3. So I've got 240 thirds plus 40 thirds. That looks like 280 thirds is B. And that's great. You know I like answers that look like that. But let me take ahead and look at the decimal. 280 divided by 3 is 93 and 1/3. So this is at 93 and 1/3. And what's great about that is that's what B is. That's what my y-intercept is. What's fabulous about that is when I go back and look at the graph, that's exactly where I predicted it should be. We said it should be between 90 and 100. So we can write the equation of this line of fit. The equation is y values are, my slope was negative 20 thirds, so it's negative 20 thirds times x, and then plus 93 and 1/3. Or you can leave it as 280 over 3. So this is the line that's attempting to model this situation. Not a lot of data was collected. I wouldn't put a lot of faith in this model, but it's modeling the data that we did collect. And the final question is, it says, predict the test score of students who exhibit 5 tired behaviors during Professor Saxum's math class in a week. So if I was to look at this, right, they're asking, hey, if you consider this line, right, where x is 5, about what do you expect to see for the score for that person? And I'm going to go ahead and I'm going to use my calculator for sure, but I'm going to take the calculator, I'm going to enter negative 20 thirds, and I'm going to multiply that times 5, and then I'm going to add to that plus 93, 93 plus 1/3, 93 and 1/3. And when I do, I get, that's amazing. It totally just worked out that way, that for my model, when I plugged that in, I ended up getting a value of 60. So your answer would be totally, it could be not a whole lot different. It's going to be somewhere around 60, but I'm predicting that for 5 tired behaviors, we might expect a score of 60%. All right, moving on to our very, very last question. It says, number 13, draw a slope triangle and use it to write the equation of the line shown in the graph at right. Okay, here we go. Draw a slope triangle. So I'm going to add a little slope triangle here. I've got, I think I'm going to go, I got a little green. My rise from this point is green. And then I've got this run, and I'm marking it red. I'm going, my y value starts at 9 and goes up to 16, right? So that means that I have a change of 7 units. 9 plus 7 is going to put me up at 16. And I can see that x is starting at 2 and it moves over to 4. 2 plus 2 more would give me 4, so my run is 2. That means the slope of this line, right, the slope is 7/2. I go up 7 over 2 units. Now, if I want to create the equation of this line, I'm going to pick either one of the points, and it honestly doesn't matter which one. Just to get things moving, I'm going to go ahead and pick this point. This point has both an x value and a y value, and of course we already know our slope, right? We know our slope parameter is m. So thinking of a linear equation in the form y equals mx and then plus b, we know that y is 16. My slope we said was 7, 2. And again, this y just came from this point, right? I'm just using this. This is a point that lives on the line, so this xy is a valid substitution into this equation. I'm grabbing the y from that point, which is 16, and I'm also grabbing the x from that point, which is 4. And then I write the plus b, oops, not times or equals b, plus b. 7 halves times 4. Let's see, 7 divided by, or 4 divided by 2 is 2. This should be 14. So I've got 16 is equal to 14 plus b. And if I take away 14 from both sides, I get that 2 is b. b is 2. So b is 2. That's great. b is 2 is my y-intercept. And I can see it. Yeah, it looks like it could be around 2. Notice it didn't mark it exact, right? So it could have been like 1 and 7/8 or something like that. So we really need to take a look at this closely. But now I know both of my parameters, right? My two parameters are my slope parameter, my y-intercept parameter. And I can write y is equal to slope parameter, which is 7 halves times x, and then plus my y-intercept parameter is 2. So y equals 7 halves x plus 2. All right, guys, I know quick 26 minutes, but that is the homework set that goes from question 8 to 13.